In this video, we're going to continue our discussion of vectors. Let's, before we do this problem, go back and take a look at what we have talked about. We started with just thinking about what vectors were used for. These are some places where vectors are used. We talked about some terminology with the vector, the head and the tail, and how to name the vector. And what makes two vectors equal to each other. They don't have to be in the same location. They just have to have the same direction and the same length. A couple definitions there. We talked about multiplying by a vector by a scalar. So if this vector is v, then 3 times v is going the same direction, but it's just 3 times as long. If we have a negative 2v, that's going to be going the opposite direction, and it's going to be twice as long. Then we did some problems here with these two vectors and talked about how to describe these different vectors in terms of u and v. Again, talking about scalar multiples. Then we talked about a vector in standard position. All these vectors here are equal to each other. But in standard position, that tail of that vector is at the origin. And when the tail of the vector is at the origin, then we can describe the vector by the location of the head of the vector, which is at the point 3, 2. And we would write it like this. But all these vectors here would have the position vector 3, 2. And then we talked about adding some vectors. We did an example here. We never did this one, so let's go ahead and finish this one. So we did u, and if I wanted to graph the opposite of w, I know the vector w is at 3, 4. So the opposite of w is going to be -1 times the vector 3, 4, which is going to be the vector -3, -4. So let's take a look at what that looks like. Let's see, I got w in red here. So -3, -4, you see, is going in the 180-degree opposite direction as w, but it's the same length of vector. Now if I want to do u minus w, I can take the vector u, which is -2, 9, and I could subtract the vector w, which is, where's the 3, 4. Or I could think of this as u plus the opposite of w, which we found here, and I can do the vector u plus the opposite of w, which is -3, -4. So either way, I'm going to get the vector components by subtracting the first component and the second component, or adding, depending on which way you write it. So this way is -2 minus 3, or -2 plus -3, that's -5. And 9 minus 4, or 9 plus -4, which is +5. All right, so if we graph that vector, -5, +5, 1, 2, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, that would be here. All right, so that's the vector u minus w. So here's the vector u. Right, and here's the vector minus w is going this way, right? This is minus w in standard position. I'm going to shift this vector minus w up here and put the tail on the head of u. That's minus w. So this is u minus w, which gives me the vector u minus w. And this green one, if I did u plus w, this gives me the vector u plus w. All right, then we talked about some algebraic properties of vectors. You can see when you're adding vectors, you just add the components, and addition is commutative. So we get all these nice commutative properties, distributive properties, associative properties of vectors, all of our nice properties. All right, so let's take a look at example 3. Let w be the vector 3, 4, u is the vector -2, 9, v is the vector 0, 16. What is the vector 2 times u? I'll just put a little vector symbol here since I can't make it bold. Plus 3 times vector v minus vector u. Well, because of all of our properties, we can just use the components, and it just becomes a pretty easy distributing, adding kind of a situation here. We'll just substitute all these things in. And we want to go component by component. So 2 times this vector is negative 4, 18. And 3 times the vector 0, 16 is 0, 48. And then we just have this vector. So now when we're adding or subtracting vectors, we're just going to do each component. So we have our horizontal components here. We're just going to combine those together. We got to subtract that one. So our horizontal component, we've got negative 4 plus 0 minus negative 2. That's all these guys, right? And then for our vertical components, we've got 18 plus 48 minus 9. Let me just figure out what that is. 18 plus 48 minus 9. We'll do some higher mathematics here to finish this up. Let's see, negative 4 plus 2 would be negative 2, and 18 plus 48 would be 66. Take away 9 would be 57. So that would give you this vector. So this whole thing right here is some vector. And the way you could think of it, if you could graph all these out, you know, you'd have, I'm not going to do this in the direction that these are, okay, but like let's say you have 2 u's. Let's say this is u. So this is vector u, and then you add 3 v's. Let's say v's going this way. Vector v, vector v, vector v. That's 3 v's. Then subtracting u would be going back this way, because this is vector u. So the result of all that, this is where you started this process, 2 u's plus 3 v's minus a u. And this is where you're ending that process. So this vector right here would be 2 u's plus 3 v's, take away a u. For whatever direction, you could put this on graph paper and do that out, but I'm just giving you a visual of what that vector means. So all this stuff right here is just really representing one vector. So a place where you might see an application like this would be in a problem where you've got the velocity of an airplane. Let's say this is the direction the airplane's trying to head and how fast it's going, but the wind is blowing this way. So the actual path of the plane is going to follow v plus w. V sub a plus w is going to give you the actual path and velocity of the plane. And we'll do some problems like that. All right, so we've seen when we're adding vectors together, if I want to do u plus v, I start at u, I end at v, and this is my u plus v vector, and we get this thing called the parallelogram rule. So if you put u and v both in standard position, then the vector u plus v is the diagonal of the parallelogram formed by those two vectors, which is kind of cool. It's the long diagonal, I should say, because we're going to see something here in a minute. All right, so if I have vector v and vector u here, and I want to find u minus v, I could think of that as u plus negative v. So this is the resulting vector u minus v. So let's say I have u and v in standard position here. So here's u minus v. Makes a triangle, right here. But it's also the other diagonal of the parallelogram. So remember we had this diagonal here. In this parallelogram, this long diagonal was u plus v. And if we wanted to find u minus v, that diagonal would be here, going this direction. That would be u minus v. That might be a little bit hard to see in this picture, but here's the vector u. I don't really have enough room here, but if I did negative v, it would go down this way, right? Negative v. So then u minus v would be this vector here, u minus v, and all we've done is just shift it up here. So u plus v, if u and v are in standard position, u plus v is the long diagonal here, and u minus v is this diagonal. That's kind of interesting. All right, so let's do a similar thing as what we did in a previous problem. Describe the following vectors in terms of w and v. So it'd be a good idea here to pause the video and see if you can figure what these are in terms of w and v, and then start it again when you have your answer. All right, let's take a look at OP. So I want to go from O to P. And this is vector W right here. So I'm going to need a W, W, and then 3 V's. 2 W's and 3 V's. So I'm going to say it's 2 vector W's plus 3 vector V's. That's similar to what we did before. All right, how about OQ? Well, one way I could get from O to Q along this path would be do a V, 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 and then this way. Now W has to go up, right? So if I'm going down, that's going to be a minus W. So let's write this one out. So I have V, and another V, and another V. But now I want to go this way. So it's not quite W. Because it's going this direction, it's minus W. So the vector OQ, which goes from here to here, could be expressed as 3 V's minus a vector W. Or you could go, you could go this way first if you wanted to. Negative W and then add 3 V's. That's the same thing. What that's showing is the commutative nature of adding vectors. We can switch the order of this addition and we get the same answer. All right, how about R to Q? So you want to start at R and you want to go to Q. Let me erase some of this. So we want to start at R and we want to go to Q. Let's see. We're going to have to go, that's a V, but it's the opposite direction of V, so that's a negative V. And then I got to go this way. That's a W, but it's the opposite direction of W. So it looks like I'm going to need a negative V minus 2W. Or if you wanted to do your minus 2W's first and then your negative V, that would be fine as well. All right. So we know a vector is really defined by two things, its magnitude and its direction. And what this last example that we did, this graph paper, is really showing the direction of these and the magnitude, which is this distance between these lines, okay? So how do we determine the magnitude of a vector? That's what we want to talk about here. So the magnitude of the vector is simply its length. So if I look at this vector here, starting at the point P, the vector PQ, starting at the point P and going to the point Q, not in standard position, okay? Let's say this vector is not in standard positions because this point P is not at the origin. You can just think of this as a triangle, right? I could make a little triangle. The magnitude of this is how long this vector is. Basically, what is the distance between these 2 points? So it's really just an extension of the distance formula. So this side of this triangle is this x2 minus x1, and the height of this would be y2 minus y1. And if I just do a little Pythagorean theorem here, I would say that x2 minus x1 squared plus y2 minus y1 squared equals d squared. Do the square root, both sides, and you get this. And that is the magnitude. So the magnitude of PQ is denoted with these absolute value signs. But we don't say absolute value, all right? We read that as the magnitude of PQ. Simply the length. So here's kind of an official definition. If given the points P and Q, vector PQ would have these components. And the magnitude denoted this can be found by using this formula. That's not a new formula to you though, right? It's not a new formula. It's the distance formula. Now if that vector is in standard position, then whatever the components of that vector are going to be the magnitude. So you may be given just a vector in standard position, and then you can find the magnitude quite easily. We're going to do an example in a second with the points not in standard position, but let's say I gave you the vector and I tell you the components are 1, 2. It doesn't even really have to be in standard position. It might be floating around somewhere else, but these components tell me what it would be in standard position. So I could simply find the magnitude of that vector by doing the square root of 1 squared plus 2 squared, which is the square root of 5. All right, so think about what this would look like. You've got 1, 2, got your vector here. That's the vector 1, 2. So all we're doing is finding the length of this side here, which is the square root of 5. That's all we're doing. So if we're given the vector by its points instead of by its components, then basically what we have to do is we have to find the components by subtracting the x's and subtracting the y's. But let's just go ahead and do a little graph so we can get a picture of this. So I'll just do a rough graph here. -5, +6, say that's up here somewhere. And 0, 8 would be just a little bit above it, say up here somewhere. Okay, so that's our vector. It goes from P to Q, so it's going this direction. And we want to find the magnitude of that vector. So we simply have to find the x component and the y component. The magnitude of vector PQ is the square root of the two x values subtracted from each other. So this is -5, this is not drawn to scale, right? This is -5, this is 0, so this distance here would be 5. Now you could do -5 minus 0 or 0 minus -5. It really doesn't matter because you're going to square it. I mean, it's nice manners to do it in the same direction, so if I go -5 minus 0 for my x's, then I would go 6 minus 8 for my y's, but it doesn't matter, really, in this case. All right, so we get the square root of 25 plus 4, which is the square root of 29. And that is the magnitude of that vector. Pretty straightforward. Well, there are a couple vectors that are very important and useful, and so we actually give them special names. We've been using names like vector u, vector v, vector w pretty loosely to just represent generic vectors. But when you see these two guys right here, vector I and vector j, those mean the vectors 0, 1 and the vector 1, 0. All right, so those vectors have special names. I can't, if I'm talking about the vector I, it only means the vector 1, 0. So it's telling you a unit vector, which we haven't really defined unit vector yet, but a unit vector has length 1. We're going to do that here in a second. A unit vector has length 1 in the horizontal direction and length 1 in the vertical direction. All right, so let's see how we could use these unit vectors to write the vector PQ as the sum of I and j. So let's remember vector I, and this notation is bold, so since I can't really make it bold, I'll use my little vector notation. So that's in the horizontal direction, and then vector j is in the vertical direction, 0, 1. All right, so here's -5, 6 again. So go ahead and plot those out on your paper. Actually, you can use your graph paper from above if you have the notes. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. And then 7, 8. Okay, so here's the point P. Here's the point Q. Here's my vector PQ. So what we want to do is we want to write this as the sum of the vectors I and j. Well, this is kind of like what we did before, except the vector I is this vector right here. It's the unit vector in the horizontal direction. So how many vector i's do I need here? Well, it looks like I'm going to need 5 of those. Right? So I'm going to need 5 vector i's, and then we got to go up to, it's kind of small, hopefully you can see that. That's 2 vector j's. And if I add those together, that should give me vector PQ. All right, let's try it out. So if I have 5 vector i's, vector I is 1, 0, and 2 vector j's, that's 0, 1. So this is going to be the vector 5, 0, which is really just giving you a vector, you know, this long, and the vector 2 or 0, 2. If I add those together, I get the vector 5, 2, which is the vector PQ in standard position. If I move this vector PQ down in standard position, 1, 2, 3, 4, 5, up 2, this would have components 5, 2. All right, so here we're just writing it in terms of the vectors I and j. All right, so we're going to use our vector PQ from before. So we still have the vector PQ, which has components 5, 2. And we want to find a unit vector, 2 unit vectors parallel to this vector PQ. So again, let's define unit vector. A unit vector is a vector whose magnitude is 1. Unit vector has magnitude 1 equal to 1. So that's your unit vector. All right, so let's draw our PQ in standard position. 1, 2, 3, 4, 5, 1, 2. So here's PQ. All right, so a unit vector in the same direction as PQ is going to be parallel to PQ. So basically what we want to do is we want to take this vector, we want it to go the same direction, except we want to, or it could go the complete opposite direction. Remember back at this definition, 2 vectors are parallel. Oops, let's try a highlighter. 2 vectors are parallel if they are scalar multiples of each other. So if you take a vector like v and you multiply it by 2v, or multiply it by 2, it's going to look like this. But I could also multiply it by -2, in which case it would look like this. So it could go the complete opposite direction. By complete opposite, I mean 180 degrees the opposite direction. And these would be considered parallel. All right, so we're trying to find a unit vector that's parallel to our vector PQ. And so it could go the opposite direction. It could go this way, which is where we're going to get 2 unit vectors. So the first thing we have to do is we have to shrink this down to a magnitude of 1. Our vector PQ, if you remember from before, did we do the magnitude of this? Well, I think we did. So our vector PQ, remember, has magnitude now that it's in its component form. I think we did this before when it was just in its point form. Has magnitude square root 29. So if I want to shrink this thing down to a magnitude of 1, then what I'm going to do is I'm going to divide each component by the magnitude of PQ. So the unit vector is going to be 5 divided by the square root of 29 and 2 divided by the square root of 29. So that vector is going to go in the same direction, except it's going to have a magnitude of 1. It's only going to have a length 1. Let's see. Let's call this vector u for unit vector. Let's see if it really does have that magnitude. So the magnitude of vector u, if I wanted to find it, I would do the square root of 5 over square root 29 squared plus 2 over square root 29 squared. This is supposed to come out to be what? If it's a unit vector, it's better come out to be 1. All right, let's give it a try here. So we'll do this out. We get 25 over 29 plus 4 over 29. It's looking good. I'm going to get the square root of 29 over 29, which is 1. All right, so to find a unit vector, you're going to divide the components by whatever the magnitude is. So let's write a generalization for that. So let's say we have a vector v that has components a and b. Then the unit vector parallel to v would have the components A divided by the magnitude of V, comma, B divided by the magnitude of V. That's a V. That would be the components of the unit vector in the same direction as V. Well, this problem asks us to find two unit vectors. So the other unit vector, we could just go the opposite direction. All right, we could just send it this way. So to do that, that's just -1 times this red vector. So we can take the opposite, let's do a different color. Well, I already did it in purple. The opposite of vector u would have components -5 root 29 and -2 over root 29. All right, that vector also has a magnitude of 1. I don't think it'd take too much convincing here. If you put negatives there, that would come out to be 1. And it is parallel to our vector PQ because it is a scalar multiple. It's actually being multiplied by 1 over square root 29. All right, we have one more example to go through in this part. I think I'm going to do that in a separate video.